In this lecture, we examine what is referred to as a dielectric. A dielectric is an insulating material that is placed in between the plates of a capacitor. Up until this point in this unit on capacitance, we've been assuming that the space in between the two plates is a vacuum. Of course, that's not the case. In an actual capacitor, the space in between the plates is filled by an insulating material that's referred to as a dielectric. Okay, now there are two ways in which we could picture situations involving dielectrics. Let's first of all envision the following. Let's say that we have a vacuum in between the plates of a capacitor. We subsequently charge up the capacitor, and then a dielectric is inserted. What happens when this occurs? So let's approach dielectrics first of all from that standpoint. Okay, so let's begin by charging up capacitor. Okay, so very simply, right here is a battery that has voltage V. Right here is my capacitor, like so. Now let's say that the capacitor initially has a capacitance C0. When we charge it up, we give it a charge we're going to refer to here as Q0. And then in between the plates, of course, we have an electric field. Right here is an electric field like so. We're going to refer to this electric field as E0. Okay, now the voltage here we're going to refer to as V. This is equal to E0 multiplied by D, where D, of course, is the space in between the two plates. Okay, and now while the capacitor is still hooked to the battery, now we insert a dielectric material. Still hooked up to the battery. We will now insert a dielectric material. Before we do, however, let's also write down the following relationship. The charge Q0 here is equal to the capacitance C0 multiplied by the voltage V. Okay, now while the capacitor is still hooked up to the battery, this means that the voltage V is maintained. So therefore, the voltage V is maintained. Okay, now I'm going to draw a close-up here of the capacitor when we insert the dielectric material. Okay, so here's a close-up of the capacitor like so. Once again, initially it has the charge Q0, like so. And then we have the electric field in black, E0, like so. And let me put a vector symbol here associated with it like this. Okay, now how can you envision a dielectric material? Well, picture a dielectric material, an insulator, as consisting of various dipole moments, because I then take those dipole moments and I place them in the presence here of this external electric field. A torque is going to be exerted upon those dipole moments such that they begin to line up preferentially in a specific direction. So let's begin to picture those dipole moments in the following way. So here's a dipole moment P associated with the dielectric material. Here's another one like so. Notice that I am pointing all of those dipoles in a preferential direction such that the positive side is here, kind of being attracted to the negatively charged plate, if you will, and the negative side is here, being attracted to the positively charged plate, if you will. Once again, once you insert the dielectric material in between the space between the two plates, a torque is going to be exerted upon those dipole moments, causing them to all line up preferentially in this direction. This then means that those dipole moments now have an induced electric field associated with them. I'll draw it in green. Which way on the diagram, however, does this induced electric field point? Well, if preferentially the positive side of the dielectric is down here and the negative side is up here, this then means that the induced electric field points upwards on the diagram like so. So we end up here with an E induced, and this is due to the lined up P dipole moments. Therefore, there is now an overall electric field, the sum of these two, the original E naught and the E induced. Let's just refer to that as E. So now E is the net E field. This is equal to the original E naught plus the E induced. Now, of course, the E induced, remember, points in the opposite direction of the E naught. This then means that in terms of its magnitude, the net electric field E is less than the original E naught. Like so. However, keep in mind that the voltage is maintained. Remember that the original voltage up on the top board, V, is equal to E naught times D. If the induced electric field, however, causes the net electric field to be less in magnitude than E naught, but this has to be the same, what then has to happen? Well, what has to happen is that charge has to flow from the battery to the capacitor's plates. This will then strengthen the overall electric field such that it is once again equal to E naught. It has to be, because remember that the voltage is maintained. So in order for the voltage to be maintained, charge has to flow to the capacitor's plates. Such that the net E field, once again, equals the original E naught. Okay, this then means that a new value of charge is present on the capacitor's plates. Let me just go ahead and redraw the situation. So now when I redraw the situation, actually let me keep the E induced here. Like so. When I redraw the situation now, there is a new charge on the plates that's referred to as Q. So basically, electrons basically flowed in this direction from the battery to this capacitor plate, and additional electrons were pulled away from this plate here, thereby giving it a greater amount of positive charge. And then therefore, the net electric field that is now present is equal to, once again, the original E naught. It has to be, because once again, the voltage is maintained, and we're not changing the separation between the two plates. So the black electric field that I drew here earlier is now once again equal to E naught. Like so. Okay, so then what changes if the charge changes? Well, keep in mind up on the top board that the original charge was equal to the original capacitance multiplied by the voltage V. The voltage V is the same. So then therefore, if this is now a greater value than it was before, the Q is greater than the Q naught. This then means that the capacitance has increased. The value of the capacitance now is greater than the original C naught. There is a linear relationship that describes how the capacitance has increased from its original value. Here's then how we describe that. The new capacitance, C, is equal to the old capacitance C naught multiplied by a number that's referred to as capital K. Capital K is called the dielectric constant. The dielectric constant is basically a measurement, if you will, of how much polarization takes place within the dielectric material when you insert it here in between the two plates of this capacitor. The greater the polarization that occurs with the dielectric, the greater the dielectric constant, therefore the greater the capacitance. It's useful to examine the situation here in terms of energy storage as well. So let's go back up to the top board for just a moment. And let's refer to the potential energy that is stored in the charge-up capacitor when it's a vacuum here in this space as U naught. This would be equal to 1/2 C naught times the voltage squared once the capacitor has been charged up. What now happens with the new value of the potential energy stored? Well, the new value of the potential energy stored is 1/2 times the new capacitance multiplied by the same voltage squared. And this new capacitance here, of course, is greater than the old capacitance, where this number here is a number that's greater than 1. I should indicate that over here, like so. It's equal to 1, of course, when talking about a vacuum, but for a material such as a wax or a waxy paste, that's typically what's used as the dielectric in an actual capacitor, the number is, of course, greater than 1. Therefore, the new value of the potential energy that is stored within is greater than the original value. So then therefore, when we actually build capacitors, we do so with this dielectric paste, as it's called, that is in between the two plates. It's already highly polarized. So then therefore, because it is highly polarized, this then means that you always hook up a capacitor in a specific way in a circuit to take advantage of that already present polarization. And then therefore, the greater the amount of polarization, the greater the dielectric constant, the greater the amount of energy stored. Now, this is the easiest way to picture a dielectric. Once again, we started off by charging up a capacitor, keeping it hooked up to the battery, and then sticking in the dielectric into the space. There's another way to think of it as well, and this is what happens if you charge up the capacitor, unhook it from the battery so the charge is maintained, and then insert the dielectric. Let's take a look briefly at that situation. Okay, so if I called the first situation 1, let's call this here situation 2. Okay, so we'll once again begin by charging a capacitor, and we then have the following. Okay, voltage V, electric field E naught. Okay, now I'm going to refer to the voltage here as V naught, like so, once we've charged the capacitor, and then we have the charge Q naught and negative Q naught, like so. Once again, the original charge equals the original capacitance and then multiplied by the original voltage. Okay, in this situation, however, if we now unhook the capacitor from the battery and then insert the dielectric, the charge remains the same. Therefore, as we'll see, the voltage has to go down. Okay, so now, just to describe that, this is 1/2 C naught V naught squared. Okay, so now, we'll unhook the capacitor from the battery. So then therefore the charge will be maintained. And we then insert the dielectric. Okay, so now here is the isolated capacitor. Like so. It's still the same charge Q naught as it was before. Once again, we've unhooked the capacitor from the battery, so the charge will be maintained. Okay, and then we insert the dielectric and the polarization takes place again and blah, blah, blah. So here are the individual dipole moment vectors like so. So we then get the E induced pointing in this direction, like so. And then therefore the overall electric field is equal to the original E naught plus E induced, and then therefore the magnitude of the new electric field is less than the original. But keep in mind that the charge here is the same. Okay, now because the charge is the same, charge is equal to new capacitance and then multiplied by a new voltage. That new voltage has to be written like this, such that these two K's cancel each other out, and you end up then with the same amount of charge Q naught as we did before prior to unhooking the capacitor from the battery. So the voltage has to go down. This makes sense, and the reason why is because the electric field magnitude has gone down. It is now a lesser value than the original value of E naught. Once again, all of this happens because charge cannot flow away or to the capacitor's plates. If you've unhooked it from the battery, the Q has to be the same. So then therefore you end up with an overall weaker electric field here between the two plates. That's this weaker here electric field than originally what we have, and then therefore the new voltage is this value here, V naught over K. We can then calculate, if we wanted to, the potential energy stored in this situation. It would be 1/2 CV squared, but now this is going to be a lesser value than it was on the top board. The reason why is because we have 1/2 times K C naught, but then times V naught over K quantity squared. If you do the math here, you end up with the following. A lesser value of potential energy than before. And the reason why is because once you've unhooked this thing from the battery and you then insert the dielectric like so, basically this charge here, the electric field associated with, does work in torquing all of these guys here to point preferentially in a specific direction. And then therefore the work that is done results in a decrease in the potential energy stored. So then therefore we would always want to have the dielectric in place to begin with, basically, whenever we hook a capacitor up to a battery.